Hello, good morning once again to advanced algebra students here. We're ready to go on and take a look here at today's work, which is our tangent function. So we're moving on to 13.6 and we're going to look at our tangent function. Now we're going to take a couple days in 13.6. So today what we're really going to focus on is just two straightforward simple things with regard to the tangent function. One thing is we're going to understand what the graph looks like and be able to work with the graph. There are really only about 3 questions you're going to have to work with the graph on. And then we're going to review again finding tangent ratios for different angles when the angles are measured, particularly in radians. Now, based on how you guys did on the trig worksheets, I'd say you probably need to review this and pay close attention as we look at how to find these tangent ratios. All right, so first let's look at the tangent function. Just like with the sine function and cosine function, we can take a trig ratio and we can turn it into a function where we let our input, our x value, be the theta or the angle, and the output becomes the ratio number. Now remember, with the tangent ratio, we know when we take an angle, a theta, and we consider that ratio, the way we get the ratio is we compare the opposite side to the adjacent side in our triangle. So what we can do is we can treat this when we look at, if we want to think of it in terms of the coordinate plane, remember when we make those reference triangles, the opposite side becomes the y value and the adjacent side becomes the x value. So as we look at that, this is in the coordinate plane here. Now, when we go to make it a function, this x represents the theta. It represents the angle. And this y here represents what happens when you take the y and divide it by the x. So it's the ratio that comes out like that. So when you do this, you get a graph that looks like this. And you may want to, my suggestion is to listen to the description and then pause the video and create the graph. So here's the description. So what happens is when we look at our opposite over adjacent sides, when we look at that unit circle, what we find out is that when our x or our theta is 0, remember if we look at our unit circle here, if I was to draw in, I'll go ahead and I'll draw in. So if I draw in a unit circle, when our theta is 0, I'm right here. So my opposite side is 0, my adjacent side is 1, so I'm at 0 there, 0 over 1 is 0. That's what the tangent ratio is. As I progress up here, as my angles start to get bigger, and I start to move in this direction here like this, remember that's the x value here in my function is this angle. This theta here is equal to my x value of the function right there. Like that, as I progress along there, notice my y values get bigger and my x values get smaller. So as I create triangles as I go along, my y values get bigger, my x values get smaller. So what happens is my fractions here are getting bigger. So notice my y values, the value of my fraction, when I divide the y coordinate by the x coordinate, it gets bigger. So as I go along here, as my angles get bigger, my fractions get bigger, and so my graph goes up like this. As I come to pi over 2, an interesting thing happens. At pi over 2, my denominator, my x coordinate, is getting really, really close to 0. And so my fraction becomes things like, say, 1 over 1/10. Well, 1 over 1/10, 1/10, when I divide by 1/10 is just 10. And then if I go 1 over 1/100th, I would get 100. And so as this gets closer and closer to 0, this whole fraction gets really, really big, goes to infinity. And that's what's happening here. We get this vertical asymptote because at pi over 2, we would get a constant over 0, which you remember, a constant over 0 in a function produces this vertical asymptote here. So the function goes like this as it goes up towards infinity as the x value or the angle gets closer to pi over 2. Immediately to the other side, once again, my x values are still very small, but they're negative. So what happens is it's still going towards infinity, but now it's going towards negative infinity. So it starts down here, comes up at pi. The y coordinate again is 0. There's no opposite side, so we're back to 0. And it keeps making this cycle. Notice it makes a complete cycle. Starts here, goes up, comes this way. When it gets back at pi, then it starts to match that again. Or we could think of it as going from pi over 2 to 3 pi over 2. So it makes its complete cycle in just pi. So it actually has a period of pi. It's a little bit different type of function. Okay, that's the graph. We'll talk a little bit more about what we're going to do with the graph later. Now let's just go back and let's review how to find tangent values. So tangent of pi over 6. If you don't like radians, change it to degrees. Pi over 6 is like 180 degrees is pi, divided by 6 would be 30. So it's the same thing as saying tangent of 30 degrees. On the graph, we can make a triangle there. Tangent of 30 degrees is right here. So this is our reference triangle, short side, long side, hypotenuse. So the tangent is the opposite over the hypotenuse, 1 over 2. Sorry, I said that wrong. Tangent is opposite over adjacent, 1 over radical 3. So we know it's 1 over radical 3. We can write it like this, but usually we just write it like this. We only do this to it when we get a radical 2 in the denominator, and we rewrite that as radical 2 over 2. All right, that one's pretty straightforward. But these start to get more complicated when we start to go angles bigger than what fit in a right triangle. So angles bigger than 90 degrees. So when I go 5 pi over 4, a lot of times this is easiest to think of as a mixed number. Instead of thinking of 5 over 4, turn it into a mixed number. Okay, so the mixed number for 5 over 4 is 1 1/4. So I want to go 1 1/4 pi. So 1 pi would be 180 degrees, and then I go another fourth. So here is my 1 pi, and then another fourth of a pi is another fourth of the way around here. So that'd be 1/4, 2/4, or 1/2, like that. Or we can just convert it to degrees and simply go that this is 180, and then 1/4 of 180, another 1/4 would be another 45. So we have this 45, 45, 90. We know this is 45 right here, so we know our sides are 1, 1, and radical 2. The difference is we have to put in the signs for the x and the y. So this x is negative. This y is negative. So when I go to find the tangent of 5 pi over 4, it's -1 over -1, which then simplifies to just being 1. All right, let's look at another one. Let's look at the tangent of -5 pi over 4. So this is like -1 1/4, so we have to go in the other direction. So we do the same amount of rotation, but we're going in the other direction. Notice when I'm here, I'm still at a 45, 45, 90, so I'm still in the sides 1, 1, radical 2. But this one here becomes +1. This one here is negative because it's negative in the x direction. So when I set up my ratio, it's opposite 1 over adjacent -1, which is 1 over -1, which is just -1. All right, let's look at another. So for the tangent of 5 pi over 2. So once again, this is like, if we turn this into a mixed number, this is like 2.5 pi. So to go 2 pi is going to be going, if I start here, it's going to go 1 pi, 2 pi, and then another half pi is going to take me right around to here. So that's 2.5 pi, one full rotation, and then another half of 180 degrees or 90 degrees, and I'm right there. Well, right there, when I go to look at my triangle, notice I have no opposite. So it's like this form here. Notice I did not put in equals. You can't say it equals 1 over 0 because this is not a number. It's undefined. Can't have a 0 in the denominator. So the answer there is undefined. The opposite side would be 1 in the y distance, but there's 0 in the x distance, so it is undefined. All right, let's look at E. E is the tangent of 3 pi. So we go here to go 3 pi. We start here. We go 1 pi, 2 pi, 3 pi. And so we're right out here. So our opposite side, our y distance, is 0. And our x distance, we can just make -1. So that's 0 over -1. That's not undefined. You can take 0 and divide by a number. It is 0. So our tangent there is 0. All right, last thing is going back to the idea of graphing. And so if we look at our basic form for a tangent graph, what we see here is that the period is pi over b. So in a normal, something like y equals tangent of x or y equals tangent of alpha, where b is 1, we have a period where it's just pi. So let's look at one like f, where we have this, and they'll ask us to find the period of this function, and they'll also ask us to find out where two asymptotes are. And the two that we want are really the one on either side of the y-axis. So what I do here, the period is pretty straightforward. I use this formula, put 3/4 in for b. Well, if I want to divide by a fraction, I multiply by its reciprocal. Multiplying there, that doesn't reduce, so I just get 4 pi over 3. That's the period. Now, since the tangent function, if we look at this, is centered at the origin, if I scroll back here, if the period is 4 pi over 3, notice what happens here. The period is pi, so I go 1/2 pi in this direction, 1/2 pi in that direction. Here, the period is 4 pi over 3, so I divide this in half, and I need to go, if I divide 4 pi over 3 in half, that's 2 pi over 3. So I go 2 pi over 3 to the right and 2 pi over 3 to the left. So easy enough to find the asymptotes. They are x equal to, when I go 2 pi over 3 to the left, it's -2 pi over 3. And 2 pi over 3 to the right is 2 pi over 3. All right, that's it. So your homework is going to be 8 through 15. That's just finding tangent ratios for angles. It's something we've already done, but it's more of that. And then 18 through 20 are finding the period of the tangent function and going ahead and describing where its asymptotes are. Okay, hope that goes well. If you have a question, you can email me or send a message in Google Classroom. And if not, we'll see you tomorrow, sort of.